So this week we're going to discuss transistors, a rough model of that, and in understanding the transistors we also need to take into account this more fundamental element called capacitor. The reason this is important is because we're going to use this to understand the timing, the finite amount of time it takes for transistor to work, even though we're going to use it in a more idealistic way. A transistor is a switch for us. And so we're going to use the switch to build gates later on. That's the plan. So this is a very simple model of these transistors. And these are, in general, what's called MOSFET, or metal oxide semiconductor field effect transistors. And if we have this notion of a functioning of a logic gate, then we can start to build more complicated circuit element, and that will lead us to functional units. In a way, you can think about them as components for calculators. So again, we want to build these higher complexity systems, a contraption if you wish. One of the components that you already use in, let's say, a simple a light device is a switch to control it on or off. And in fact, that is the only thing that we need to build modern computers, a switch. A switch is a three-terminal device that has two ends that connects to other circuit elements, like over here, that's your two ends, right? And we want these switches to be controlled by other things, so there is a control end, and that's what we're showing over here. So the semiconductor device that we're dealing with is sort of this thing that if you apply a different signal, let's for now assume that that's just a voltage. If I change the voltage between high and low, if I can adjust the semiconductor device property so that at some point it's acting with very low resistance, that I can approximate it as a conducting circuit. It's a piece of wire. And at another point, it's high resistance, so it's off. And that's what it is. So on, off, black, white kind of thing. And of course, if I have other element, this would already work. I have power supply and some sort of appliance. We will see that this is precisely what people have invented. The whole history of semiconductor devices, very long, and you will hear about it again and again in device courses. Here, I'm going to give you an oversimplified model of what a MOSFET is. And even this is only one type of device, oversimplified. So as the name suggests, it has metal over here, oxide, which serves as an insulator. Usually we build silicon devices and some other application domain. Sometimes they use other material as the main material, but for most part, the general purpose electronics or computing devices are based on silicon. So these are silicon dioxide to serve as an insulator. And then you have the body. This is usually just silicon with some doped material. It's a semiconductor device, which means it's not quite insulator and it's not quite conductor. And you can actually change its behavior dynamically by increasing the charge concentration, the charge carrier concentration, and this is a lot of fun. So again, oversimplified model, what can we do? If we apply a high voltage relative to the body, okay, so that's the control gate, you can imagine field line going down to the body, which is grounded, or sort of relative to the high voltage, it's the low voltage. You can imagine why free electrons will want to move towards the region, against the field line of the electric field. So that may change the concentration of this area right under the insulator. part. Because of the insulator, these electrons wouldn't go across the barrier. So then I have an abundance of charge carrier over here. And when that happens, this part of the device, shown here in darker color, is actually acting more like a conductor. And if you have, voltage differential, then the charge starts to flow in this region. So this is how it works. And if I get rid of this high voltage, in this case, the lines disappear, the charge return to their original positions or more equally distributed across the body. This little area under the insulator is no longer highly concentrated, and this channel, the conducting channel, disappears. So the three-terminal device that we have over here appears as if it's in an off state. So that's roughly how it works. Not exactly how. And the device doesn't really look like this. It's more like that. By the way, the name is just very long. Metal oxide semiconductor. That's referring to the sandwich structure. Metal, the oxide over here, and the semiconductor down there. And the effect is created by the electric field, so it's a field effect transistor, which means there are other type of transistor that we're not even interested in this class. So that's how it works. The way these are built in reality, it's more like this. It's not just 3 layers. The interesting part is the 3-layer. That's your gate. Usually not really in metal. It used to be a lot of the times in so-called polysilicon, but you can think of it that's metal to apply the field across the barrier, the oxide, and then here is the channel. This is your channel. To connect, to allow current flying through the channel, you build some wells. These are heavily doped so that they act more like a metal in terms of connecting things. And you have contacts. These are usually metal, so you can take these 2 nodes to connect them to other components. And we have all kinds of symbols for them. I personally would just draw something like that, indicating the 2 sides over here that gets connected or disconnected, controlled by the gate. Okay, that's your 3-terminal device. In fact, there are so many details that will fill entire courses. Notice the plural about how they work. There are enhancement mode, depletion mode, and newer ones that people keep on inventing. So for instance, one of the issue is when we turn a transistor off, they're not completely off. Okay? These are ideal case, we call them a switch, but they're not really a switch. That's what they really are. It's a semiconductor device. So the channel is not completely conducting as a piece of ideal wire or completely shut off. When they're conducting, in fact, there is resistance. When they're not conducting that well, in fact, there's still current that we don't want. It's called leakage current. So newer devices tend to try to wrap around the gate. In this case, one of the big new development in the chip industry is this gate that wraps around this thin layer of silicon shown in gray over here. So we call that a 3D, like having fins. So they're called FinFET. Traditional planar devices, the gate is right here, like left-hand side, just sitting on top. Now the gate is wrapping around the channel, which is like a fin, so it's being wrapped around, controlled better, and when we want to shut it off, it's shut off. So that's how it goes. And you can see some picture, the 3D view. A chip comes in a flat structure, that's the silicon. Everything else, this is the color. This color over here shows what your chip comes in initially like. It's big substrate of a bunch of silicon, nothing else. Then you start to dig a well, by doping the material, sometimes using this mechanism, sometimes that mechanism. You etch channels to deposit metal or this kind of semiconductor. From the top view, it's a lot of work that you do to the chip. Three-dimensionally speaking, they look something like that. And if you cut it off from the side, this is the view. So it's a very messy process, by no means simple. Building one of the newer fabs to fabricate the most advanced chip would cost billions of dollars. It's certainly not a cheap enterprise. And here's one example of a finished product. You can kind of see the patterns being laid out on this big wafer. So the little pieces are stamped there with the pattern from your design, and then go through tens of steps of processing, and eventually you can cut them into smaller rectangular pieces called die. So that's a die, and fabricate or package it with heat sinks on the top. This is one of the high-end chip that goes into a server. It's quite big, as you can see on the right-hand side. So it burns a lot of power, but there are also smaller chips for maybe consumer device. This is a iPhone chip that's kind of small. It's really magnified over here, but if you open up a phone, there's a package inside. It's more complicated than just a chip. Is in fact a system in a package with not just the CPU but also memory, sort of 3D packaged together, and in the future they may be actually fabricated from a single entity rather than multiple separate dies and then later on combined into a package. You'll learn about this in electronic courses to know, what is the trend, the new problems, the new solutions. We're gonna take a very simplistic view of them and just use them as semi-idealized switches. So why switches? What can we do with it? Well, let's start with this. We do this exercise. If you don't remember, pause the video, think about it. Suppose we're digitizing the voltage. We don't care exactly what's the voltage. So if it's high enough, let's say we're operating in a 1 volt power supply, so anything above 0.75, we call it high. Anything below 0.25, we call it low, suppose. So then the question here is, if VI is high, meaning high enough, what is the output of VO? Okay. At this, you can just use your KCL, KVL equation sort of exercise. You don't have to set up the equation to know the exact current or whatnot, but it's very easy to see. If the VI is high, we know that this sort of device, it's an NMOS device. We talked about it when voltage is high, when this control side is high, it's a closed circuit. It's a closed switch. Imagine it as a piece of wire. So okay, then current would flow in the circuit, and the I across this is just V over R. As a result, since this is a short circuit, we don't even need to know the I. We know the voltage across is 0, okay, or close to 0. What if we, can we clean that? What if VI is low? Then this is open circuit. This is as if nothing exists there. It's open circuit. Then there is no current flowing through the resistor. So the voltage drop according to Ohm's law is 0 volt. There's no voltage across the resistor. And if I go around the circuit, then all the voltage has to drop on the output port. So V out is high, or just call that 1, logical 1. So what is that? If input is low, the output is high. If input is high, the output is low. What is that? That's a inverter, a NOT gate. Okay, the output is the opposite of the input. That's a piece of logic. It works, right? If we abstract away the voltages and the current, this is a piece of logic that we can use to build more complicated logic. Okay, so that's what it is. If we ignore the detail, this is an inverter. Okay, what about using this inverter to drive another one? Like that. Well, if one of them forms an inverter, wouldn't the second one be another inverter? And two inverters chained together logically would dictate the output VO is going to be the same as the first input. And you can try this out. It's not very difficult. It's really exactly the same process. When V1 is high, this is short circuit. So V2 is going to be 0. It's going to be low. Therefore, this doesn't exist. So V out is going to be high again. Conversely, if V1 is low, this doesn't exist, then V2 is just like that, and that's going to be high. Okay, and as a result, the output is going to be short-circuited, and therefore the output of V out is going to be 0. So yes, it worked. We can chain them together. Okay, so you can have a more complex circuit. In this case, it's not very interesting. Two inversions give you the original, not interesting at all. But we can start there. So now the problem is this good? And again, if you haven't done this, think about it. What is what is bad about it? So the reason this is bad is very simple. We use this as a logic device. Suppose we just want to know what is the inversion of V1. Okay, that's the logical. We send an input of 1. We want the output to be 1. That's our computing device. Once we figure this out, we don't want the circuit to burn power or to burn a lot of power. But if in this particular case, no matter what input V1 is, if it's 1, V2 is going to be 0. If it's 0, V1 is going to be V2 is going to be 1. So one of the device, it's either this one or that one. One of the device has a high voltage controlling the channel, which means, let's pretend it's this one, which means this is going to be short-circuited or connected. The switch is on. Then there's going to be constant current flow in that circuit. And the current is V over R, if this resistance is R, if the voltage supply is V. Okay? Or the power of that is V squared divided by R. Constant. We're not doing anything to it. We send you an input, you give me an output, and I'm done with it. The power is on. I'm not turning the entire chip off, but I'm not sending you more information to process. So that's bad. We don't want constant power. This is not doing work. It's just generating heat. So if you think about a possible solution, what we wanted is really this. Why do we have the resistor over here? Well, that's a load, if you wish. What if I turn that to 0? It's a problem. If this is just a piece of wire and V1 happens to be high and that's a piece of wire, then I burn my power supply. The current would be too high. So we don't want that. We don't want this current to be high. That's why we have this load. So, but if you think about it in another way, maybe looking at this, when Vi is high, we're connecting this output node to ground. That's why it gives us a 0 volt. But when Vi is low, we're connecting this sort of to that. That's what we want, to give us the high volt, right? The fact that we have a resistor there is really just to make sure when this short circuits, or when this is connected, the current is not so high. So we don't need the resistor as any functional thing. It's limiting some bad thing. So basically when this switch is on, we want to make sure we limit the current over there. What else does that for you? The answer is it's a switch. If this is on, we can have something over here that acts like a switch that is off, then we did our job. Okay, so that is really what we can do. Have two switches, except let them work in the opposite way. If one is connected, the other is on. If the other is connected, this one is going to be off. Then at any moment, this node is either connected to the ground or the positive side of your power supply, and that will give you the correct voltage. And the way you do that, it so happens a P-type MOS device can do exactly that. So the way this is connected is like this, and a PMOS device, I'm just going to use a symbol with a little circle at the gate to indicate that it's being controlled in the exact opposite way, if you wish. If there's a high voltage over here, then there's a high voltage over here, then this sort of this symbol for inversion kind of tell you that, oh, without it's sort of like in an NMOS, the equivalent of in an NMOS, you have a low voltage. So in a PMOS device, when the gate has high voltage, because the body is in fact, what we're not drawn, is in fact connected to the power supply. So when the input has high voltage, the voltage across the channel is actually 0, and that's when the device is off. Okay, never mind the details, which you will encounter in different classes. Suffice it to assume this model, which is high voltage on for NMOS, low voltage on for PMOS. Okay, so if we use that, we can actually create a complementary pair of switches operated like this. And now imagine what happens if the input V, let's just look at this V2, if V2 is 1, this is going to be connected. The switch is on here, but off there. Good. Then the output is going to be 0. It's grounded. If the input is, if I can erase that, if the input is 0, on the other hand, then this is gone and this is on. The switch is on. So now my output is tied to V. So that gives me the same functionality as the inverter that I did with just one transistor, with the NMOS transistor. But I don't have a constant current flowing through the circuit at any time. So that's good. And this is called a complementary MOS circuit, or CMOS circuit. And it's precisely done to save power. And in fact, in the early stages of the computer age, we have NMOS computers where we only use one transistor, so the chip is perhaps smaller. I may be wrong in that, but That may be an advantage in some sense. The chip is cheaper to make, but it burns more power because it doesn't have this property that at any time only one device, only one of the switches is on, so there is no conducting path from power to ground for any long duration. In fact, for a split second, when both of them are turning, because the device will all operate, right? So this time it may be on or high, let's say V1 may be high. At some future point, the high may be transitioning to the low, and during that brief moment, one of the devices is trying to close, the other device is trying to turn on. You might have an overlap where both are somewhat on, and in fact there is a current in the analysis of the circuit that's called short circuit current. This does exist, but in the steady state, not in the transient. In steady state, with CMOS, we don't have a conducting path. Okay, this is again an oversimplification. If you look at how the threshold works, there is the sub-threshold leakage, there is a gate leakage, there's some leakage, but the intrinsic steady state mode is that there is no current in steady state. So that's a good thing. So now, let's think about what really happens to the gate. How does the gate actually change its voltage? What is the gate? And this is, in fact, a device that you've probably heard. It's a capacitor. Why is it a capacitor? Because we have two parallel plates. We have the metal on one side, oxide or insulator in this region, and below that, it's the channel. This channel is, in fact, can be viewed as another plate. And this is your parallel plate capacitor. So if you've seen this device in the past, it follows, just like a resistor follows an Ohm's law, it follows its own law. And that's Q equals CV, the charge accumulated on one side of the parallel plate. So if you can count the amount of the number of ion or electron, that Q is proportional to the capacitor's capacitance, C, and the voltage across the two plates. So Q equals CV. That's its Ohm's law, if you wish, the circuit elements property. Now, so the capacitance of this is a function of a couple of things. First, the permittivity of the dielectric, of whatever is used to fill this. So this could be air, this could be some insulator, whatever it is. It's proportional to area. The larger it is, you need more charge to fill it, and it's inversely proportional to the distance. Okay, and you will learn about this in the circuit course. How does this derive? I'll give you a very quick sort of derivation later on, but that's what it is. C is a constant. Given a device, the device doesn't change. It's a constant capacitance. But when it operates, the Q may change depending on what the voltage is, or the other way around. The Q decides the voltage, but they're always the same proportion. Q equals C times V. So we know how to write KVL equations, right? There are currents, there are voltages. That's what KCL, KVL is. We don't know anything about charge. We never know about charge resistive network. Okay, no problem. We can get current. Current, by definition, is just the rate of charge flow. In other words, it's dQ over dt. Unit time charge change. Put in a different way, if Q is CV and C is a constant, then you can take dq is basically C, you can take out of the differential, and then you get I equals C times dV dt. So now you're setting up an equation that is no longer a linear equation, it's a differential equation. It's no longer an algebraic equation. So we can write KCl, KVL, except now we're writing differential equations, okay? And we will see how to solve them kind of just intuitively later on, but now I want you to see a little bit about how this thing really works as a parallel plate capacitor, as a load. So let's think about, I'm driving here, right? This is, I have V1 over here with the resistor. It will change V2, but how does it really do that? How does, let's say initially V1 is 0, so V1, or maybe let's start with 1, so V2 is 0. This is low. And now I give a different input. I change the input to 0. Let's say instantaneously, suppose. How does V2 react to that? So if I draw the if I draw V1 as time goes by, this is V1, as time goes by, it goes from 1, zoop, to 0. If I want to see what happens to V2 as a result of that, does it go, because when V1 is 1, we know V2 in steady state should be 0. Does it go straight up? Is there a delay? Does it wait a little bit and then go up? Does it go up gradually in some way? How does that work, right? That's what we're interested in for now. So we have to look at the circuit. What is it? And we see that this device is connected to these two transistors. Every one of them is a parallel plate capacitor. See? Because this is grounded. This side is connected to power supply. And that's what we have. We have a charge path through this transistor, right? We're talking about going from 1 to 0 for V1. So gradually, this is going to be my charge path. This channel is not an ideal switch, so there's a resistor there. And then I have two parallel plate capacitor. One is the gate capacitor. There are more than that, but let's just focus on the gate capacitor. This capacitor over here, let's call that 1, and there's another one over here, let's call that 2, so 1 and 2, okay? And we're charging those capacitors. That's really what it is. And when the charge reaches final state, and it will stay there, that's when V becomes high. So initially it's 0. Initially V2, if we look at V2, initially it's 0. Maybe I can change a color. It's initially 0. It's initially 0, and it somehow is going to be charged too high. It could go linearly up. It could go kind of exponentially towards this point, or maybe gradually tapering to that position. We don't know which one. We'll develop an intuition in just a moment, but it's charging. It's not instantaneous. It doesn't go instantaneous. Why? Because if it goes instantaneously from 0 to 1 volt, then dt is 0, and dV dt is infinite, and that means we need infinite current, which is unrealistic in non-ideal circuits. So, but now we want to know, okay, what happens if I have two capacitors connected in parallel? What is the effect of that? If this guy has a capacitance of C1, this guy has a capacitance of C2, can I use one to replace them? And the answer is yes, and it's just KCL, KVL equation. Okay, we know from KVL that if they're connected in parallel, the voltage across C2 is the same as the voltage across C1. So I use 1V, I don't say V1, V2, I would just say, okay, the current that flows into C1 is I1 equals C1 dV dt. Same thing, I2 equals C2 dV dt. And according to KCL, if I clean this out, there is I1, there is I2, right? So the I, that the charging current that comes in, I is the sum of them, which is C1 plus C2, which means if you look at this, if I look at this as an equivalent circuit, there is I, which is just I1 plus I2. It's proportional to, according to our derivation, is just C1 plus C2 dV dt. That's a constant, because both C1 and C2 are a constant, dV dt. So if you look at that, this is the same as if I have one capacitor whose capacitance C equivalent is just C1 plus C2. Okay, so parallel capacitor is just adding. Similarly, you can derive if it's series connection, then it's like the parallel resistor. It's the inverse of the capacitor. That's the sum. The sum of the inverse of the equivalent series capacitance is the sum of the inverse of the two capacitance. You can do this, it's the same kind of equation that allows you to derive that. So now, we can, it really doesn't matter because we just need the parallel connection. That's what we have. So the circuit looks like this, okay? It's some charging resistance in the channel, and we're trying to charge an equivalent parallel capacitor. So the circuit is an RC circuit. And let's say I close this at time 0. That's an ideal circuit. Boom, I close it. What happens? At time 0, what is the voltage across when this is off? When the switch is off. Okay, when the switch is off, is there any current flowing through the circuit? No. Therefore, voltage, there is no charge in the capacitor, and Q equals CV, and V is 0. Okay, so this is your steady state. Now I am turning this on. So voltage at 0 time is always 0. Now suppose I turn this on. I charge the capacitor. What is the steady state? What is the long-term result? Can this voltage be higher than that of the power source? The answer is no. Okay? Because if the minute they reach parity, the voltage over here, that's V equals that V, then there is no current already through the resistor. Okay, that's Ohm's law. There's no current. And so you stop charging it. If you don't have current, then you have no change. If I is 0, then there is no change. dq has to be 0. dq dt has to be 0. So over time, Q doesn't change. So Q reaches a constant, and therefore V reaches a constant. Okay, so because of that, you can already tell that it has to be one of these two curves. That, or I guess it can be this as well. It can reach a point and stop. But another intuition will tell you how fast you're reaching it. At the very beginning, just after time 0, okay, here, what is the voltage across C? It's very small. It's close to 0. So V at time 0, t equals 0, is 0, okay. Now, if this is 0, what is the voltage drop across these 2 points? The resistor has to be, let's call this VDD, the power supply. Has to be VDD, plus, minus. So current goes that way, right? This is just KVL. So at that time, I is just VDD over R. It's whatever the current would be if this is just a resistive circuit with power supply and the resistor. So that's an I. So at that point, it's a slope. We're charging this device with current I. So therefore, as time goes by, the voltage is going to go like that. Okay, it's linear. As time goes by, total Q on the capacitor is just I times T. And you will get something like that. But wait, what if we charge a little bit? We're here. Or we're here. Let me zoom this out. We charged a little bit. Now we're here. After some time, this time is so short that I can just assume this little delta T over here. Delta T over here. It's linear. After this time, what is the voltage across? This is my voltage, right? This is T. What is the voltage across the capacitor? It's not 0 anymore. Then at that time, what is the voltage across R? It's no longer V. It's V minus VC, or VDD. That's the power supply's voltage, minus VC. So it's smaller. And therefore, the I is smaller. Okay, so by that much, that's accumulated. So now, for the next little delta T, it's a bit smaller than before. And the one after that, a bit smaller still. And so on and so forth until the V of the capacitor approaches the asymptote, which is VDD, because once it gets there, the current will completely stop. But will it really get there? Will it ever get there? The answer is actually no. It takes an infinite amount of time to actually get there because we can write the equations. It looks like this. Okay, so C times dV dt. Remember, what's dV dt times C? This is dq dt. This is really I. This is the I that flows through the capacitor. And according to KCL, this is the same I that flows through the resistor. So the resistor's voltage drop is this, I times R, plus that of the capacitor, that's this component. Together, they're equal VDD. Okay? Which is a constant. So if we put them together, it's really R times C times dV dt plus V equals some constant VDD. Okay, so this is a constant, this is a constant, and the rest is a differential equation of V. And here we want you to use your intuition. What function is like that? What function plus its derivative is some constant? Another way of thinking about it is you can remove it. What function's derivative is itself? Okay, dividing by some constant plus some constant. Okay, what function's derivative has that sort of form? As an exponential function. an exponential function's division is just a constant time of its original function. And so you can have other constants. So the general form is this. This is an fx. Its derivative is just a times itself plus some constant p. So then the fx is just an exponential function, maybe with some constant and then a factor in the exponent. And then you can set boundary conditions and try to solve this. If you did all your work, you're going to get something that looks like this. Okay? Or sometimes we write it in a simpler way. It's VDD times 1 minus an decaying exponential function, e to the minus t over tau. Tau is the constant. It's a constant. Sometimes you hear the term the RC constant because it's literally the value of R times C. So if you look at the units, the resistor unit ohm times the capacitor's unit farad, it's in fact that of time. So an exponential function like this can be drawn like that, and you can remember some factor that in 1t you will decay in 1 tau. This would be minus 1, e to the minus 1. It's about 27%. You go down to 37%. You go down to 63% of the original difference. So the original is 100%. Now you're 37% away from that. And another tau happens, so you're getting a 37% decay of that 30%. If you multiply that together, 37% of 37% is about 14%. And so it goes like that. So every tau time unit later, the difference to the asymptote is 1 over e times the original one. So that's what it is. Okay, so why do we care about this? So if we want to solve this equation, we can, but really what is the most important, what matters is that the device that we're creating has resistor. We want the channel to have 0 resistor. Ain't gonna happen. We want the gate capacitor to be really small. That's not gonna happen. These are all unwanted and they're called parasitics. So even with this simple circuit, the steady state solution, the reality is there is this charging path that is an RC circuit, and it takes time for, even when, let's say, one node has a very sharp voltage transition. Okay, it goes, as time goes by, it goes from 1, boom, to 0. Let's just say that's the case. That's is your input. Then your output, let's say it goes up. It's going to start to go up in a curve like that. Of course, I'm exaggerating this. In reality, this curve might be so fast that in some time unit it looks like it's sharp enough. Okay. So the computer speed is limited by the transient, and that's the most important takeaway. That this is really what's happening. We need time to charge the next stage's capacitor, and sometimes we need time to discharge them so that they can drain, and it would be the same thing. Suppose the output voltage is high and we made it go low, it's not going to go straight down. It's going to go in an RC decay, exponentially decaying function. Hence, your computer is not infinitely fast, even though they're plenty fast today, operating in gigahertz. That means all of these are much shorter than a time cycle, than a clock cycle of a gigahertz or multi-gigahertz. The clock cycle is in the hundreds of picoseconds. So one of these transitions better be much smaller than hundreds of picoseconds. Otherwise, we won't get much done in one clock cycle. Anyway, so the most important takeaway is these transistors are not ideal, and therefore from one stage to another, if we can go back to the logical view much early on, if we have, let's start here, if we have one stage, it changes. The next stage is going to take time to react. So if even if the input goes from high to low exactly, very sharp, if V1 goes like that, V2, if we lay it on top of another, we will see that it goes up in a finite curve. And in fact, even this is simplified analysis. So in reality, there is that, and trigger the next stage to have some delay before it starts to gradually change. So from one stage to another stage, it gets, we start to change here, we get to steady state here in the input, but we only get to, let's say, steady state a little bit later in the next stage. That's why there's finite speed propagation. It's not infinitely fast. Okay, so that's really the most important message for this. But from now on, we're just going to keep this to the back of our mind to say, okay, that happens. It's not infinitely fast, but we're still going to look them primarily as switches with ideal behavior. So we're going to skip all of that. Next time, we're going to build logic gate. And when we're looking at them in logic gates, we're mindful of the fact that they don't operate in infinite speed, but mostly we care about the steady state. The input is this, then the steady state output is that. So for an inverter, for instance, if the input is 1, the output is going to be 0. But if I really look at the voltage of input, I'm going to see as the input goes from low to high, the output is going to suffer some delay before it goes from high to low. So there is a finite delay. We draw these things like that with very square edges. In reality, they're all curved. But again, when we focus only on the steady state, we will say, oh, the input of this gives the output of that. And that's what we'll discuss next week.